A matrix function can look terrifying. Square the matrix, exponentiate it, or pass it through a polynomial, and it seems like the eigenvalues should be hard to predict. The spectral mapping theorem says something surprisingly simple. The eigenvalues just move through the same function. Here is the clean finite-dimensional version. Let it be a square complex matrix, and let P be a polynomial. The spectrum sigma of A is the set of eigenvalues, the lambdas where a minus lambda I is singular. Then the spectrum of P of A is exactly P applied to the spectrum of A. The first half of the proof follows the eigenvectors. If a V equals lambda V, then a squared V equals lambda squared V. And in general, A to the k V equals lambda to the k V, therefore P of a times V equals P of lambda times V, so every P of lambda is an eigenvalue of P of A. For the reverse direction, start with an eigenvalue mu of P of A, that means P of a minus mu I is singular. Now factor the scalar polynomial P of Z minus mu into linear factors, then substitute the matrix A into that exact identity. The left-hand side is singular, but if every factor A minus alpha J I were invertible, then their product would be invertible too. So at least one factor is singular. That means alpha J is in the spectrum of A, and because P of alpha J equals mu, the eigenvalue mu came from P of the original spectrum. Now both directions are done. The eigenvector argument gives P of sigma of A inside sigma of P of A. The factorization argument gives sigma of P of A inside P of sigma of A. The two inclusions combine into equality. This is useful because the theorem turns questions about matrix functions into questions about points. In broader versions, it applies to functions such as the exponential. Sigma of e to the t A is e to the t times sigma of A. That is why it appears in stability, differential equations, filters, and numerical algorithms. The takeaway is simple. A function of a matrix cannot invent spectral points out of nowhere. It can only move the old spectral points according to the same function, and that turns hard matrix behavior into geometry in the complex plane.